Okay, hi everyone, and welcome to the run through for Lab 7. Actually, though, we're going to start here in Lab 5 because although Lab 7 goes a little bit into this, I wanted to cover this topic from the bonus section in 5, which is on tables. Now, tables are pretty simple in R at the end of the day, but nonetheless, they're a little bit tricky, and it's something we haven't really explicitly addressed in the labs yet. But it's probably going to be useful, will definitely be useful for the second assessment, and maybe even for the one coming up this week. Now, in this Lab 5 script, you can see here we're using the Pokemon data from week 1 or 2. So I'm just going to load that in. I've already set my working directory here. And the code for a table is really quite simple. So here we've just got table, and then we've just added a variable. So the function here is table, and then we add a variable in. Now we're going to do all of this in base R, because actually, although we can create some more complex tables using tidyverse format, and we will look at that. Actually, for basic tables, the base R way is probably a bit easier and better. So we've got to use our data name and extract to get this variable, but then we just need table. So I'm going to run this, and what we've got is table of type 2. Now, if we look at the variable, here's type 2, and it's a character variable that specifies something about the type of Pokemon we're looking at. When we run a table on one variable, this is what our output looks like. Now, this is actually going on to 2 lines, so R will sort of print this out. So depending on the size of your console, it's going to look a bit different. So if I run it there, it'll run to the end of the console and onto a second line. So that can make them a little bit hard to read if we've got lots of different categories as we have here, but hopefully it's something we get used to looking at. So what you can see table has done then is it's counted the number of occurrences of each unique category within the variable. So we've got 3 bug Pokemon, 20 dark, 18 dragon, 6 electric, 23 fairy, and so on. So this is a good way then, if we were asked a question like, how many of the Pokemon are of a given type, right? We can run a table and we can read off our result from here. Another question we might be asked, though, is, well, what proportion of Pokemon are of a given type? Now, this is, again, pretty easy to find for any individual one of these. So if we take Fairy, for example, we've got 23 Pokemon. And, of course, we know we've got 800 observations in total. So it would be 23 divided by 800 and multiplied by 100. Well, or actually, we don't really need to do the step at all. So 23 divided by 800. And there we go. We've got about 2.8%. So around 3% rounded up. But we have a way of doing this more simply, and that's by using this bit of code. So this is prop table or proportions table. So proportion, percentage, we can kind of use those words interchangeably. So if I run this then, so we've got our table is embedded within this. So we create the table first and then convert it to proportions. So if I run this, we can see we've now got the percentage of the total sample made up by each categories. And you can see here, fairy, we just calculated that, 0.28, and here it is. But we can calculate it for everything all at once. Now that's one use for tables then. We can get some simple answers out for that. The really useful thing, though, is this, cross-tabulation. So this is when we start adding 2 variables into our tables, and we can see which observations fit into the same mix of categories. So in this case, then, we're going to take type 1 Pokemon and Pokemon. So you can see we're separating this with a comma, but we've just entered 2 variables into table. So if we run this, then what we've got is, so this variable legendary is a binary variable. So false for no, they're not legendary, true for yes, they are. And so here we've got the number of bug Pokemon that fall into each category. So we've got 69 non-legendary and 0 legendary. For Dragon, we've got 20 non-legendary and 12 legendary, and so on down the list. So we can start to get a sense of where parts of our data intersect. So there are no bug Pokemon, very few dark Pokemon, but a significant proportion of dragon Pokemon. Now again, we could use this just to read off individual answers. We can even use it to create a new data set if we wanted to. But what happens if we use proportions table on this? Because we might also want to know, well, what proportion of the data do each of these categories represent? And the code here is the same. So we've just got table, proportions table, and if we run it, here's what we get. Now, this generates it with a few decimal points. It's a little bit difficult to see what's going on here, but what we've got here is we've got the proportion of the entire data set composed of these individual categories. So those 69 non-legendary bug Pokemon are around 8.6% of the total sample. Those dragon Pokemon, which are non-legendary, they're about 2.5% of the sample, but the legendary ones, about 1.5% of the sample. Now, this kind of prop table, we actually probably wouldn't use it that much. But prop table can do one other interesting thing, which is, what if, for example, we wanted to know which of these types of Pokemon has the highest proportion of legendary Pokemon? Or what if we wanted to know what percentage, what category of Pokemon has the highest proportion of legendary Pokemon? So we might want to calculate instead across a row or down a column rather than all at once. Now, we can do this with a really simple option in prop table, but the simplicity of this option is often what trips us up. So in these two prop tables, you can see we've got a 1 on the end of this one. So we go comma 1 or comma 2. So what are these doing? Well, they're specifying whether we go across rows or across columns. And in this function, it's 1 for row and 2 for column. So if I run this, we can see now we're calculating across the row. So we've got 100% of bug Pokemon, 93% of dark Pokemon, but only 62% of dragon Pokemon fall into this category of false. So if we sum up across the row, we should always get to 100%. And with a little bit of work, we can work down here and say, well, which Pokemon has the highest proportion of legendary Pokemon? And we can see here it's actually dragon. So 50% of it, no, sorry, not dragon, of flying Pokemon. So 50% of flying Pokemon, 0.5, you can see I've highlighted it there, are legendary. So it's the proportionately most legendary type of Pokemon, at least using this type 1 variable. We could also do it the other way, though. So what if instead we wanted to know what is the largest proportionate category within legendary Pokemon? So if we add a 2 to the end and run this, it's now our columns, so moving downwards here, that sum to 100%, or to 1 in this case, if we're representing percentages this way. So now if we read down this column, let's have a look. It looks like psychic Pokemon actually make up the greatest proportion overall. They're about 20% of the total legendary Pokemon, over 20%. So we might ask, notice then we're asking two different questions there, or answering two different questions. So here we're asking which type of Pokemon has the highest proportion of legendary, and here we're asking which Pokemon represents the highest proportion within the category legendary. Now that is a little confusing, both because the option here is so similar, it's either 1 or 2, and we might miss it off altogether, and that would again be an error, depending on the question we're asking. But we also have to interpret what the right answer to the question is. And this is something that I've seen in assessments before. People routinely get this wrong. Again, not because they don't know what they're doing, but just because it's really easy both to put the wrong number on the end or to interpret the question wrong and to answer it backwards. So to answer, say, psychic when we should have been answering flying, or vice versa. So a really simple bit of code in a way, really powerful tool for answering certain questions, but also one that takes a little bit of concentration to make sure we're interpreting correctly. Now, we can create tables with tidyverse. So this function count in tidyverse is going to provide us a count like this. Now, so if I count generation, for example, we've got 6 different generations, and it will give us the n of each of these. We can also do cross tables this way. So you can see here I've entered 2 things, legendary and generation. And we've got, again, a kind of table where we're going across rows here. Now, there are things we could add to this to create proportions as well, but they're all more complicated than just using prop table. So generally speaking, if we just want to create some simple tables, we've got table and we've got prop table. And the only tricky thing, again, is just making sure if we're using prop table with 2 variables, that we're using the right number on the end of here to calculate rows or to calculate columns. Okay, so let's move on to lab script 7. Now, I'm already actually loaded Tinyverse a second ago, but I'm just going to run this again. You can never run this too many times because we need this loaded. Now, again, I've already set my working directory, so I'm just going to load in this data. If you want to go back and get a tutorial on that, I think it's in lab script 2. Now, here you can say it says make changes from last session. We didn't actually run through this, but we'll do this now. So we're using this VF England dataset here. And there's a code book for this. This is hosted on week 5. So first thing we're going to do then, we've got a new dataset we're looking through. We're always going to come and have a look at this. Now, what we can see is that this data is a survey. And it's specifically a survey on opinions on voter fraud in England. And it's a bit different from the SIMD database that we were using before, because you can see most of the categories here, or most of the questions here rather, are categorical variables. So we've only got one integer here. We've got one integer here as age. The rest of these are either binary or multiple categories. And in fact, 2 of these variables are a kind of special kind of categorical variable. Now, this is called ordinal data. So these are independent categories, but they have a clear order. So we go from strongly agree, agree, slightly agree, neither, and up this side. So these measures, actually the proper social scientific name is that these are Likert scales. And this is a pretty commonly used thing in the social sciences because it allows us to get a bit sort of better understanding of the way in which people disagree or agree. So we don't just give people 2 options, we give them 7, and we get a sense of their level of agreement and also the degree to which people have no opinion on this. And we can always recode these, and in fact this is what we're going to be looking at in lab script 7, back into binary categories. So these Likert scales, very widely used. They're usually either 7 or 5 categories. And they give us these ordinal categorical data. The first thing we're going to do here, though, is that we are going to create new variables. And we're going to do that using mutate. Now, before we were using mutate, we were using it to recode variables into usually numeric versions of themselves so that we can use this for analysis. In this case, though, we're going to be using that same structure to create new variables. So whereas before we would have, say, the variable name equals as numeric and then the same variable name, here we've got three variables that we can see are not currently in the data set. So at the moment, these are the ones we've got. These are some new ones. To create new variables, then, we need to give them some kind of content. And we can do that using some existing variables in the data set. Now, there are lots of ways we could do this, but the function we're going to look at here is this one, if-else. And whenever we get these ifs in function names, we're usually looking at some kind of conditional function. And that's the way it is here. So I'm going to go for the help for if-else. You can see this is conditional element selection. And here's the usage example. So you can see we've got three things. We've got test, yes, and no. And what this means is that we can set really any kind of test we want. And then the new variable is going to be coded with whatever we put in here, if that test is passed, or whatever we put in here, if this test is not passed. So if we look at our test then, success and failure here is going to be coded as 1 and 0. So in other words, a binary variable, right? Two categories. And then here's our test. So age greater than 49. So what we're doing is we're taking this age variable here. We're saying look through every observation. If age is greater than 49, which is also say 50 or above, we code that as a 1 in the new variable. And if it's 49 or lower, we code it as 0. And that's going to be called over 50 binary. Now, here, we've just got the same thing again. So we can see we can create multiple variables within mutate, just like we can recode multiple variables. So we just have a comma, and we move down onto this line. We'll then go if-else again. And this time, our if-else test is age less than the mean of age. So we're using another function here, in this case, calculating the mean, to then use within our test, within if-else, and within mutate to create the variable. And we're keeping that exactly the same. We've still got a 1 and a 0. Now our final one, see here, problem bin. We've got if-else, but this time we've got a more complex looking test. So what's going on here? So our test is using this VF problem variable. So let's go and have a look at that. So here's VF problem. So how much do you agree or disagree with the following statement? And these answers in our data are coded as characters. So VF problem, slightly agree, disagree, neither agree nor disagree. We can pick out these answers. So we've got VF problem strongly agree and VF problem strongly disagree. We use these double equal signs here for this. The new bit is this. We've got this little downward line. So what does this mean? Well, this is a logical OR. So in other words, what we're saying is if either of these conditions are true, we code as 1. And if either one of them is not true, we code as 0. So in this case, we're coding for observations who have a strong opinion on this. They either strongly agree or strongly disagree. So I'm going to run this all, and we're going to create these new variables. And the thing to look at is over here. So at the moment you can say this says 8 variables. And if I run this, we've changed to 11 variables. We've added 3. And usually these are going to be added over here on the right-hand side of the data set. So our over 50 bin has been coded 1 when our age is above 50. Our problem bin has been coded 1 when we have a strongly agree here. So we've been coded as 1. There's another one here, strongly agree again. But here we've got strongly disagree. It's also been coded as 1. Now, one of the good things about tidyverse then is that rather than having to write out a completely new line of code, if we want to add more variables, we can do this pretty easily from in here. So if I just add a comma to the end of this, press return, I can come down onto another line. And let's create a variable which is strongly agree on both of VF problem and our other ordinal variable VF alter. So if I want to do this, let's have, what do we want to call this? Problem alter bin. Now, then I can just put equals. I'm going to use if else again. Open my brackets, and actually, because it's pretty similar to this, I'm going to copy and paste this down to here. So here's our test, and I'm going to alter 3 things. So firstly, we're going to have VF alter here. It's the name of the other variable. Now, if I was worried about misspelling it, I could just copy it from here. And then for VF problem, what I want is strongly agree. I need to make sure I've specified my outcomes. So again, this is just going to be 1 and 0. And this time what I want is people who've expressed strongly agree for both of these. And actually for this, I can use a logical and. That's just your ampersand symbol here. So we use this to represent and in short form in text. In R, it's logical and. So both these conditions have to be true. I could also recode some other variables. So what else have we got in here? Let's look at, for example, we've got partisan identification. So this has got 3 categories: conservative voters, other voters, and UKIP or Brexit Party. So what I'm going to do is I'm going to create a new variable. I'm going to call it conservative equals if else. Open my brackets. In this case, it's PID equals conservative. So we can see here that this is coded conservative here. And then I can't forget that I need to put my outcomes in again. So I'm going to run this, and we should see, I can run this whole block again because it's just going to recreate these variables again, but we should see this jump up by another 2. So there we go, we're now up to 13 variables over here. Now, why would I want to do this? What's the point of creating these new binary variables? Well, there's a few things that we could do with this. So the mean of a binary variable is always going to be the proportion represented by the category that we coded as 1. So I could, for example, use my conservative variable that I just calculated. Oh, that's the wrong way around. So we're going to go VF underscore England. Calculate the mean here. So we can see there then that I can now say that the 27% of observations in this data are Conservative Party identifiers. Another thing I could do is I can use binary variables as part of a strategy to filter my data or create new data sets. Now I can do this with a function that we looked at in one of the lab run-throughs, I think in some of the labs this week, called filter. Now if I want to do this, I'm going to create a new data set. So to do that, all I have to do is change this. So this doesn't exist yet, but it will after we run this code. Come down onto the second line, and I can use filter. And then all I need to do is filter on a variable. So when conservative equals 1, we're going to keep those. Now if I run this, you can see we've dropped down to 550 observations, all of which have a party ID of conservative. But I selected that on the basis of my new binary variable. I'm going to close that down because I don't need it. So lots of reasons then that it's good to create these binary variables. We could also put them into more complex kinds of analysis. But the main thing to learn from this is this mutate function, we can do all sorts of things inside it. So if I come to the end here, you can see it's grey highlighting this bracket and this bracket. So this is all inside of mutate, just separated by these little commas on the end of the row. Okay, so we'll come back to some of those variables in a bit, but the other part of this lab is that we've got some more Ggplots. Now, last time we only looked at one kind of plot. We looked at a scatter plot, and we did that because it's good to demonstrate how correlation works. It's the appropriate visualization for the correlated R and R squared from our correlation. But there's all sorts of other things that we can create, all again within this this function ggplot. So one of these is a histogram. Now histograms are often mistaken for box plots when we see them in the wild, but actually, or bar graphs rather, not box plots, when we see them in the wild. But in fact, they're a bit of a different thing. So what a histogram does is it allows us to visualize continuous data by separating out that continuous data into different categories and then counting how many fall within that category. So in this case, we've got age here. So our standard format for ggplot, VF England, piped into ggplot, and then we select the variables we're going to use here. Now, last time we selected 2 variables. For a scatter, we need 2. For a histogram, we only need 1. We've then got a plus on the end of the line, and then we just add the chart type here. So we remember that all of those chart types begin with geom underscore, and then something on the end to specify it. So here we've got geom histogram. So I'm going to run this, and you can see we've got a plot here. And this is broadly showing the distribution of ages in this data set. And what we can immediately see from this is we've got this kind of spike of observations here, fewer young people, and then age drops off around here. So we've got this, what we might call normally distributed data, but with a positive skew over here. Now with histograms, we have all sorts of color and customization options. So for histogram, we can change the color of the outline of the bars and the fill of the bars. So if we add these here, we get a nice green and black histogram. We've also got the same theme options. So here we've got theme minimal. I think we used theme line last time. but this is just a different thing that's going to change the background. We add this on another line just with a plus. So there we go. We've got a nice minimal theme now. We haven't got that grey in the background. There's one other thing here, though, that's a bit more substantive. So some of this is just about how our graphs look, but some of this is about how our graphs are calculated. And you can see the other thing we've added here is this, bins. Now, bins are what we call these individual lines on a bar graph, and they have a given width, but they also have a given number. So in this case, if I say bins 20, I'm going to get 20 of these bars. Now, the reason why I want to change that is if I have too few bars, so let's change this to 1, histograms become a bit useless, right? I'm not splitting up the data at all, so I'm just getting this big block. On the other hand, if I sort of add 1,000 bins, my histogram looks a bit messy too, so we can still sort of see the distribution here. We've got all these artificial gaps, and we're sort of turning it back into a line graph. So the trick with histograms then is to select what we think is around the right number so that we're showing the distribution of our data, but without it becoming sort of overly complex or difficult to look at. And then, of course, we've also got the ability to just add a bunch of these labels onto it. Now, this is exactly the same, plus labels, and then we've got options like labeling the x-axis, the title, the caption, and we can put whatever text we like in here. And there we go, we've got a fully formatted histogram. Now, I said a second ago that histograms are often mistaken for bar charts, but we can also create bar charts into Ggplot. So here you can see again, we've just got one variable, and we've changed it to G on bar, that being what we use for bar charts. Now, the distinction here is we use histograms for continuous data, but we use bar graphs for categorical data. So here we've got PID. This is the one we looked at a second ago. So this is party identification. And if I run this, we've got these categories. Now, bar graphs also have some unique capabilities. So you can see here we've got AES, fill, PID. And this is going to change the fill color by category. So if I run this, you can see we've now got different colors here and this legend at the side. Now, the really interesting thing, though, is that bar graphs, one thing we can do is that we can split them by a different thing. So at the moment, we've got fill of PID. But what if we changed that fill to, say, Brexit vote? So this is another categorical variable. This is whether people voted leave or remain in the 2016 referendum. And if I run this, you can see the bar graph that we now get is what we call a split bar graph. And these, again, a bit like cross tables, can be really, really useful for looking at the relationship between different variables of the data set. So you can see here that if the respondent identifies with UKIP or the Brexit Party, they're overwhelmingly likely to have voted leave. That makes sense. By contrast, if you voted for other parties, so Labour, the Liberal Democrats, the Greens, or identify with those, about 50% or more seem to have voted Remain. And for the Conservatives, it's not as overwhelming as the UKIP or Brexit Party, but we've got a predominant number of Conservative identifiers who also voted Leave. And finally, then we've got the same theme and legend theme options. One thing here, though, is I just moved that code. We've got an option here on theme that is going to remove this legend at the side, and this is something we'd want to do. So the legend is this little, sometimes called keys over here, and if we are creating a graph that just fills with one color for those, the labels are already down the bottom. So we can use this theme legend position none to just remove that entirely. So now we've got a nice bar graph showing the different numbers in these categories. Now, this is fine for this kind of variable. We've got PID. So PID, if we look at it, this is a pure categorical variable. There's no order to these. We've just got conservative, other, and UKIP. There's no logical way in which we can say that this is a higher category than this. That's not true, though, for everything in these data sets. So, for example, if we come down here briefly, I'm just going to modify this to show you how this is going to look originally. What if I did it with VF problem? So here's a graph of VF problem. But what we can see here is we've got a problem. So the ordering of this is agree, disagree, neither, slightly agree, slightly disagree, strongly agree, and strongly disagree. And now this isn't a logical order at all for this kind of variable, right? What we want is, say, strongly agree on this side and strongly disagree over here. So what can we do about that? Because this is just put it in alphabetical order. How do we change that? Well, this comes back to this question of factor variables. Now, factors is something we looked at before, and we can use mutate to recode something into a factor. When we do it, though, we have two options that we didn't look at previously. And this is that we can assign levels and labels to a factor variable. Now, levels is going to tell R what order we want these in. And that applies to when we create tables, and you've got some code for this up here, and when we create graphs. Labels then sit on top of those categories. And in this case, because this is a character variable, I'm specifying the levels, and it looks exactly the same as specifying the labels. In fact, for this thing, I could probably omit labels at all, because this is going to stay as the values. I do this with mutate. And actually, this is going to create a new VF problem factor variable. I'm actually not going to do that, though. I'm going to recode it into VF problem, just so you can see how this works. So VF problem becomes factor version of VF problem with these labels and these levels. Now, that level is set by, we've got combine here. We used this in week 1, and this is our ordered list. So we go strongly disagree, disagree, slightly disagree, neither, slightly agree, agree, and strongly agree. So if I recode this variable then, now if we looked at this, we're not going to see anything's changed, right? The variable's going to look exactly the same. So here it is, VF problem. But we can tell the difference, because if I create this bar plot now, so we've got VF problem here. These are now in the correct order. So we've got strongly disagree here and strongly agree over here. Now this is a little tricky to get your head around at first. So I'm just going to show you how to do this on a few other variables in the data set. Now, there's an easy one and a hard one here. The easy one is the other Likert scale. So if you remember, we've got another Likert scale here, VF alter. And it's got exactly the same values as the earlier one. So if it worked for our first one, then really all we need to do is we're just going to swap out the variable names. So again, I can run this. I'm going to alter this to VF alter. I'd have to change the labels, but I'm not going to do that now. But again, you can see this is now in the correct order. Let's try a more difficult one, though. So I'm going to, again, copy this just to modify this code. So there's one more ordinal variable in this data set, and it's this one, education. So education has 3 levels, low, medium, and high. This is a little more tricky though, because if we look at this, so I'm just going to run the class of education. Keep forgetting to put my data set in first. So if I run the class of education, you can see this is an integer. I could also, if I want to check this, I could also run a table. So I'm going to do, let's do a table of education. So we can see this variable then has been coded 1, 2, 3. We could also look at it up here. So here you go, education, 1, 2, 3. So now what we're going to do then is we're going to use those values here, 1, 2, and 3. But we're going to assign labels here. So our values are 1, 2, and 3. So our ordered list becomes 1, 2, 3. Up here, though, we're going to create those labels. And we know what those should be from here. So we've got 1 as low, 2 as medium, and 3 as high. So in this case, I can have low, and that's going to correspond to 1 because it's the first one in the list. Medium, likewise. Now, a third one in the list is high. So these have got to be matching strings. We've got 3 here and 3 here. 1 becomes the label low, 2 becomes the label medium, and 3 becomes the label high. But the variable actually stays coded as 1, 2, and 3. These labels just sit over the top of them. And when we create things like tables and graphs, they're going to show up in those. The last thing then is I'm just going to change my variable names. So we've got to get education and education. So if I run this, low, medium, high, and now I'm going to run my table again. You can see we're now getting those labels. They're showing up here when we create a table. And I think actually when we come to here, we're now seeing those labels here as well. But nonetheless, if I run class, this is now a factor. But you might remember if I run type of, so this was the thing that was kind of similar to class. You can see it's still saying it's an integer. So we've still got that 1, 2, 3 down there. But we've now coded it as a factor. We've given it labels and we've given it levels. And if I wanted to here, it's going to abuse this bit of code again to use education. I have to get rid of my labels because these aren't going to make a lot of sense. Let's run this, and there we go. We've got education, low, medium, high. Should show up in all of these labels. Okay, so final ggplot we're going to look at is box plots. Now these are again very useful graphs because we get a sense of the distribution of multiple variables at once. And we can do this by splitting up, say, the age variable. So this is a continuous variable by a categorical variable. So we've got X is Brexit vote and Y is age. And again, the simplest form of this, we're just changing geom to underscore box plot. And just making sure we've got 2 variables in here. So here we go. And this is telling us that the average age, so these box plots show median, interquartile range, and the full range. And you can see the median age of a Leave voter is pretty significantly higher than that of a Remain voter. So the median age of a Leave voter around 60, median age of a Remain voter probably sitting there around 45. Now, one thing we've got here is we've got missing data. So we might want to remove that, right? We don't always want that in our visualizations. And this is something we can actually do just by adding in another step here. So here, rather than piping VF England straight into Ggplot, we're piping in VF England. We're dropping NAs on the Brexit vote variable, and then we're adding it to Ggplot. So Ggplot, again, is just another function here. We don't have to use it on its own. We can drop the missing data, and then we can plot it out. And when we do that, what you'll notice is it just disappears from this graph. So we've almost created another data set just within this function, within this line of pipes, that drops NA before it does a Ggplot. And these will stay in our data set. So they're still, those observation numbers is the same over here. But for the purposes of this, using this step, we've dropped them and they get removed from our graph. We can use the same trick with all sorts of things, with tables, with anything we can think of, that we can just add in just this other little stage, and then we add another pipe and keep going. And we've got a lot of the same options here. We can fill with colors based on categories, add themes, get rid of the legend or the key, and add in labels. So these all within Ggplot, they're divided by pluses, whereas the divisions up here are divided by pipes because they're different functions. Okay, so one more thing to do on this script then. We're going to look at tables, and we're going to look at subsetting. So I mentioned, and it says at the end of last week's script, but of course that was actually at the beginning of this video, that we can use tables in different ways. We can use the base R script, but we can also do this in tidyverse. And the way we would do this is by, again, a series of piped steps. So here we're going to use one of our variables. We've got proportion over 50 here. We're going to create a new variable called proportion over 50, and we're going to do it using the mean of over 50 bin. What we're doing here, though, is creating what we sometimes call a tibble. So this is a tidyverse table. So we take our data, we drop missing on the Brexit vote, we then group by the Brexit vote. Now, when we group by, that means we're going to get separate answers for each category in Brexit vote, except, of course, NA, because we've dropped it. So we're going to get separate answers to whatever we put next for the Brexit vote. And what we've put next is summarize with a column name called proportion over 50, the mean of over 50 bin. So what we get there is this little mini data set down here. So we can see that the average proportion over 50 for Remain was 43%, 44%, and for Leave it was around 65%. Now we can also keep adding to this. So summarize can have multiple columns. So what if I also wanted prop conservative? And of course, I've got a variable for this. You remember we created this one as conservative. And if we calculate the mean of conservative, we can add to that table. So here we go. We've got the proportion of conservatives voting, or proportion of Remain voters voting Conservative is around 0.18, so that's 18%. But the proportion of Leave voters rather, who are Conservative, is around 40%. So this table then is in some ways a bit more flexible than our standard tables, because we can create counts or proportions or any other kind of calculation we want to put into summarize. It's a bit less flexible because we've got to do this stuff at the beginning. So this is something that really is going to become relevant in later assessments. You may not actually have to use this at all, but just be aware this is a good way of having these kind of results. Because equally, I could, if I wanted to, let's group by. Let's firstly drop NA for conservative, group by conservative, and then I'm actually going to put Brexit vote in here instead. And it's going to be proportion Brexit. So this is essentially a bit like when we used the prop table option, we can calculate this both ways. So if we do it this way, I've got a warning message. Prop Brexit. What did I do there? No, I know what's happened there. So there we go. This is a good example. So Brexit vote, that's not numeric. It's actually a character variable. So we'd actually have to change that. I'm actually going to do that now. Why not? So I just try to calculate the mean of this. Now this is binary, but it's actually a character variable. But why don't we just go VF England, and I'm going to create an if-else. Let's just grab the code from up here. So here's some mutate with if-else. Let's grab this. I'm going to come down to here. So our two categories are going to be 1 and 0. In this case, though, what do we need the variable name to be? Let's call it Brexit binary. If Brexit vote, spelled correctly, Brexit vote equals, and let's see how this is coded. Brexit vote is coded. Let's say, I think it's coded to dot leave, so let's just use that. So this variable is going to be coded 1 if we find that the vote is leave, and 0 otherwise. So let's run that. Brexit bin. So we've got up to 14 variables over here. And now let's change this to Brexit bin. Oh, it still didn't work. So what's going on here? Prop Brexit. Grouping by conservative. And summarizing over 50. And proportion Brexit with the mean of Brexit bin. Okay, well, what's going on here? So let's try the mean of Brexit bin. Let's see if I created this correctly. Okay, so we didn't create Brexit bin. That's a failure to extract. Let's making a few mistakes here. Okay, so we've got the mean of Brexit bin. And we're getting NA for that. So what's going on there? Okay, that's interesting. So we've got some missing data in here. So we might have to try and fix that. So let's drop by conservative and drop by, because we could drop by multiple things here. Let's drop by Brexit bin too. And there we go, fixed it. So there we go. Now we've got, the answer is that the proportion over 50 of Non-conservatives is 48%. The average age over 50 numbers of conservatives, 68. And again, we can see we've got 69% of conservative voters voted for Brexit, whereas only 42% of non-conservative voters. And that's maybe not a good, necessarily a good way of looking at it, because I've just lumped in here in my non-conservatives, UKIP and other, and we saw those were quite different categories. But that's just an example then of the kind of tables we can create. As you saw, though, I made a couple of different mistakes. There was a few things I had to fix for that to work. So these are a little bit fiddly, especially if you're new to this kind of code. But this is another way of creating some flexible tables that give us answers to some of the questions we might ask. Now, there's other ways of doing this. Now, the rest of the script deals with doing this using what we call subsetting. So subsetting looks a bit like this. And you can see this is base R because we're using extracts. So you can get into how this works if you like, but I think this is probably the preferred way. This is one of the reasons why tidyverse is useful, because it's a bit more modular. We can use this summarize to get these tables. Rather than here, you can see we're separately calculating the mean by using this, the subset of remain and leave when we calculate the mean. But summarize here gives us it in a table. Nonetheless, here you can see these same answers. We've got the mean of these two separate groups. So if we wanted to calculate the difference, run this, minus 21.6. Now I covered filter a second ago as well. I just showed you this up the top, so we won't look at this here. And the bonus on this deals with this case when reformatting, which is something we'll deal with at the beginning of the lab. So again, I won't look at this here. So that's lab 5 and 7. Again, the main thing to sort of take away from this is we've got lots of modular code now. So we've got these histograms. I can swap out the variable names. We've got if-else. I can add more if-else tests. And when we come to it, we can use the structure of these case when blocks of text or blocks of code to change things as well. So increasingly from here, the job is going to be, we're going to take blocks of code, I'm going to rewrite them to do new things. And that's ultimately going to be the most important skill when it comes to the final assessment. So I will see everyone in lab 8 this week. And we will keep working on some more advanced R skills.